Okay, 3, 2, 1. All right, so welcome to All Types of Go Types. This talk is for Go West 2020. This is the first year that we've had this conference. It fell in 2020, so we got to do it all online. But I'm still excited. I'm really excited to share what I know about Go types and kind of help you learn something new about Go. My name is Carson Anderson. I'm a DevX engineer at Weave. Just to give some background on me before we go into it, I've been working in Go full-time for about the past year at Weave. I use Go to write tools for our engineers to deploy and maintain software. Prior to that, I was also writing Go on a semi-daily basis in my capacity as a CloudOps engineer. So I've been using Go quite a bit. I really got into it to help write tools for Kubernetes and Docker and a lot of the other cloud-native tools because they're all written in Go. Go is sort of the de facto language of cloud-native right now. And it's really powerful. It's got this great type system, which is the whole point of this talk. And it makes it nice to write readable, efficient code. So let's get right into it. The point of this talk is that I wanted to answer some questions. I'm not going to introduce every single type to you. In fact, I'm not covering a few of the lower level types. I'm really covering some things that I've learned, some gotchas or weird behaviors or just unexpected things about Go's type system. So I'm not going to read all these out. You can read them on your own if you want, but this gives you an idea of the whole point of this talk is to surprise you or help you learn a few new things or avoid some gotchas about Go and its type system. So let's go ahead and dig right in. First thing I want to talk about is Booleans in Go. We're going to start incredibly simple, and it's going to get more complex as we go. I swear, bools are just where we start. It's going to get more interesting, even if you're a seasoned Go engineer. First, really easy question. Seems simple. How big is a bool? Now, we know that bools are true or false, right? They're 0 or 1. In other places, like maybe in SQL engines, Booleans typically take a bit because 1 bit is all it takes to do true or false. So if we use the size of function from the unsafe package, we can create a bool and ask how big is this bool. And if we run this, we get 1 back. Now, this seems like the right answer, right? Well, okay, let's step back and let's actually talk for a second about the unsafe size of function because I'm going to use it a lot in the presentation and we need to understand what we're getting back. When we call the size of function, giving it a type, what we get back, and I've bolded this here, is the size in bytes. So really, if we want to calculate the number of bits that something takes up in Go, we need to use unsafe size of and multiply it by 8. So we've got a slightly modified version of this function down here where we multiply it by 8 and add the word bits to be very clear of the size that we're getting. And if we run that same code, it turns out that actually, contrary to maybe something like an SQL engine, in Go, a Boolean is a full 8 bits all the time. Even though we only need 1 bit, it's a full 8 bits or 1 byte in Go. Now, there's a reason for this, and we'll cover this towards the end of the presentation. There's actually a very good reason that we take 7 bits and don't use them. But we'll get to that later. So, bool variables are a byte wide. This is the first kind of interesting thing. This is not so much a useful thing to know in Go, so much as it's just kind of like an interesting language ephemera, bit of information. Bools are not a bit, they're a full byte all the time. So now the question is, how often, we're kind of dig into ints, right? We're going from bools, I want to move on to ints. We're going to kind of start real simple and build our way up. Before I get into ints, I wanted to ask the question, okay, well Go is now, the Go language is written in Go itself. And I know that there are these numbered int. There's int 8, 16, 32, 64, but I don't use those very much. What I actually use is this first type. It's just int. This is what you see all over the place in Go. In fact, I counted inside Go source code for the language itself. Just plain int is used well and above and far more than any other explicitly numbered int type. And so this is a question I asked pretty early on in my Go career. Like, I'm using int a lot. How big is an int? How many bytes is it? How much memory am I taking up? And it seems like a reasonable question. Now we can use the size of function to figure out how big and prove that all of our sized ints are the size that we expect, right? So int 8 is 8 bits. Int 16 is 16 bits, etc., etc. This isn't a big surprise. This isn't interesting, right? We just proved that this function, this methodology of testing works, that we can run this and figure out how big the different sized ints are. But let's answer our original question. We can do the same thing. I'm going to skip by this. We can do the same thing for uints. Let's answer our original question. How big is an int? Just a plain int or a uint where there's no number at the end, right? We're going to take that exact same size of to get the bytes, multiply it by 8 to get the bits. If we run this, we get 64 bits back. So that's it, right? Answer. We answered our question. Int and uint are 64 bits wide, right? Okay, well, no. It turns out that that is correct, but it's not always correct. So let's go ahead and run that exact same code, and we're going to call out and run this command, but explicitly passing this environment variable to Go that says compile for architecture 386. So run that same code for a different processor architecture. And if we do this, instead of 64 bits like before, we actually get 32. The code has not changed. It is still an int and a uint, but now each of those represents 32 bits of memory, not 64. And the reason for this is, if we dig into the Go spec, I'm actually going to reference the Go spec several times in the presentation. I would actually recommend you browse through it, especially if you have questions about specific things. It's not as dense as you might expect. You'd think a language specification would be really hard to read. It's actually quite readable and really enlightening. So if we dig into this numeric types section, we'll find out that uint and int can be either 32 bits or 64 bits, depending on the architecture. And I've also included this uint pointer. We won't talk about it. So the short version of this is, how big is an int? It depends. What architecture are you compiling the code for? If you compile it in short for a 32-bit system, it's going to be 32 bits. 64-bit is going to be 64. Ints can change. And the question that immediately follows that for me was, well, which one should I use then? Should I use this one that can maybe be different sizes all the time? Or should I use the one that I know is always going to be a fixed size? And the standard knowledge and kind of the standard advice is, well, use uint and int for most things. That's the common thing. And then use the explicitly sized ints for data models, interoperability, things where you need to guarantee you don't overflow buffers. And the whole reason I included that count of usage of ints and the sized ints in the Go source code was to prove that this is not something we just say. This is something Go itself, when it writes itself, uses. They use int almost, more than 2 or 3 times some of the other types. So that's the standard advice. This is the next takeaway. Int and uint can change size depending on where they're compiled for. So that's something you might not expect in Go. We're going to move on to floats. I won't dig too deep, but there is one really cool thing about floats I want to talk about. First thing we're going to do is something that seems basic, really, really simple. We're going to take a float of 0.1, add a float of 0.2, and compare that to 0.3. Now, if we run it with these, and you're familiar with floating point math and computers and how computers handle floating points in general, a result of false won't actually be a surprise. It turns out that this kind of stuff is really, really normal for all languages. It's not even a Go thing. And we can dig into this more by using the printf statements to get more decimal points for these variables. Even though we declared them with just a 0.1, 0.2, 0.3, some of those are not necessarily representable as their actual values. And so you can see here, it's really obvious why a plus b does not equal c. It's because floating point math is weird with computers. That's just how floating point math works. And I won't dig into it. But it's clear here why this doesn't work. The Go part that's particularly interesting in Go is that if we change that, if we have that exact same code block, but instead of variables, we change that to a constant, we're going to get a different result. When those are constants, this now returns true, when it shouldn't. When they're variables, it was false because floating point math, but when they're constants, it was true. And going back to the spec again, it turns out, okay, well, that's why. It turns out that in the Go implementation, even though variables can be arbitrary precision, the compiler might, and the Go compiler does, choose to represent them with limited precision. So if we print this out, you can see that these all actually add up to equal a plus b does add up to equal c, because the Go compiler has a fixed definition and fixed precision for all of its floats. And I bring this up because this will not be the first time where a constant behaves differently from a variable in Go. Constants are really, really nice in Go, and they actually are very convenient and don't make you think too hard to use constants in Go, but they do have some gotchas. And one of those being that float constants can have, and in the main compiler do, fixed precision. So that's something really neat, and that might catch you up in Go. Let's dig more into constants, though. We're already talking about float constants. Let's dig into constants themselves, because I said they're interesting in Go. Constants aren't what you think they are. Looking at this code, there's actually 3 constants. Well, there's 4. And we've got really, really simple code here, right? We're going to say we're going to sleep for 2 seconds, then we're going to sleep for 2, do that, and then print done. And if we run this code, no big surprise, it sleeps for 2 seconds and then says it's done. This is something you'll see all the time in your code. Now, if we wanted to refactor this and say, well, I don't want to put the number 2 in there twice, that's a magic number and I have to repeat it, so I'm going to rip that out into a constant. And I say sleep seconds equals 2, and then I'm going to put it in place of where 2 was in both of my expressions. And if we run this, this is again not a big surprise. It sleeps for 2 seconds and then it works. But what if later down the line I say, well, it was nice that that's a constant, but I really want to be able to pass it as an argument. I want to be able to do a go run on this file and then pass an argument that says, well, okay, sleep for 2 seconds by default, have a variable called sleep seconds with a value of 2 by default. And if I gave you an argument, take that argument, convert it to an integer, convert the string argument to an integer from position 1, and then save that to sleep seconds. And then do your normal sleep, right? Really, if you rip out and don't think so much about the length arg stuff, all I really did was change sleep seconds from a constant to a variable, and sometimes I change that variable. And if we run this code, it crashes, right? We get this error, and I'm going to show you this error on the next slide. It's saying that I can't multiply a time.second which is a duration, by an integer. And this really is frustrating the first time you encounter. And this is what the first thing that made me dig into Go's type system myself. Because I would look at this code and say, well, I just changed it from a constant to a variable. How can that one change make my code suddenly not compile? And if we dig in, again, back to the spec, it turns out that most of the constants that you use in Go are untyped. Constants, by default, have no typed. They might have a type. You could explicitly say this constant is an int or an int64 or what have you, but they don't by default. And in fact, most of the constants you use when you write Go are going to be untyped. So this is one of those cases where I'm going to show you what the Go compiler does. There's actually a lot of cases where the Go compiler rewrites your code right before it compiles it to do things for you. And this isn't the first one that I'm going to show. Sorry, this isn't the last one I'm going to show. The Go compiler is effectively saying, okay, well, you've got this constant, sleep seconds, which is an untyped int constant with a value 2. And I know how to convert an int constant to a time.duration, so right before I compile this, I'm going to rewrite your code, and I'm going to cast your sleep seconds into a duration so I can multiply a duration by a duration. And it works. So if we want to do this ourselves, we can. We can have this integer variable, and because it's a variable now, and variables all have types, there's no such thing as an untyped variable, we have to explicitly do the casting ourselves, and if we do that, the code works. So this is one of those cases where changing from a constant to a variable completely changes. Just like with floats, it changes the behavior of the code with just changing from a constant to a variable or vice versa. So next interesting discovery is that constants can be untyped. And like I said, the majority of constants that you use in Go are untyped constants. Speaking of, let's talk about iota. Iota is fun because it is a very novel Go thing. This is kind of your first encounter most of us will have with iota, where we have a constant block. The very first thing is equal to iota, and then there is no value in any of the following constants. They're just repeated on new lines. And when I look at this, it kind of reads to me like, oh, well, iota is a type. I'm saying that created is an iota, and that starting is an iota, and started is an iota. And if I print all these, what I'm going to get by default is 0, 1, 2, and 3, right? And the temptation, and what I honestly thought when I first read this is, well, iota is a type. What kind of type is iota? And so that's what made me dig into this further. And it turns out that if you go back to the Go spec, the iota is an integer constant. Iota isn't actually a type. It's sort of a placeholder, and we'll dig into that. Because iota isn't a type, it can be assigned to any type. It's like an integer constant. So if I've got this code where I create A, B, C, and D, you can see that A continues to be untyped, but B, C, and D each have explicit types, all of them coming off of iota. But I don't have to do any casting here because iota isn't a type. It's just an integer constant. And then below here, if I do some fancy printing to basically print the first thing, print each variable first as a value, then as a type, we'll see that each time it goes from 0, 1, 2, 3, but it becomes the type that I'm assigning it as. It either stays untyped or becomes an int or float or what have you. And that's because iota is an untyped integer constant. What I like to think of iota as is effectively right before compilation again, the Go compiler says, I see all these iotas. Each time I see an iota in a const block, I'm going to rip it out and I'm going to put in an untyped integer that is the index of that line of the block, right? So the first, so it's going to be 0, 1, 2, 3 index. And if you saw this code, you'd know intuitively, now that we know about untyped constants, that it's totally fine to convert this untyped 0 and keep it as an untyped, or convert an untyped 1 into an int64. Like those conversions, the compiler will then rewrite those to do casting for us. And if we run this, we see that yes, we got the exact same output. Instead of using iota by hard coding those untyped integers, we get the same output, because that's all the compiler does. Because iota is not a type and it's a dynamic constant, you can actually reuse it within a single expression in the const block. You can multiply iota by other untyped constants. You can add it to itself. You can do math. You can even skip blocks if you want to force a new index number. And so if we run this, we can see that, yeah, we get, iota times 0. So 0 times 0, or we get 2, or we can kind of manipulate and work with iota. This part is a bit just language ephemera, but there are a couple interesting use cases in the Go spec where iota is used multiple times in a single line to declare, say, a byte and a bit and a bit mask, where you can take iota and then assign it to iota minus 1. I'm not going to get, again, that's a little bit out of scope of this presentation, but there are actually good use cases of using iota and then using it again in the same line of a const block. But again, the most that we see is where we see it for this kind of shorthand enumeration in Go. And the discovery that we have is, okay, iota isn't actually a type. It's this untyped int, and it changes value. It's like this, almost like a dynamic constant or a placeholder for the compiler. One last thing before we go away from iota, by the way. If you combine iota and this kind of shorthand enumeration with the stringer generator in Go, where you add a comment saying, I want you to generate, use the stringer generator, give it a flag. I can write basically that same code, run go generate, and now my prints, instead of being 0, 1, 2, are the names of the constants. So when you combine this nice shorthand iota enumeration with the stringer generator and go generate, you can get nice free stringification of your constants. So that's something I highly recommend that is great to combine with iota. Let's move on. Let's get a little more complicated. Let's dig into arrays and slices. Now, I'm not going to introduce these necessarily, but I'm going to talk about them. Arrays are, in Go, just big swaths of memory, right? Really simple. It's this much memory. This is a big chunk of memory, and you can index a value at any part of it. And we've got some sample code here where we make an array that's 50 booleans, and we can index it, and we can change the value and get that value back. This isn't super interesting, right? And we actually don't see arrays a lot in Go because they're not useful, because they're fixed by definition. Once I've made an array and said this is a 50 width boolean array, I can never make it bigger or smaller. It's stuck at that size forever. That's just how arrays work. So they're not that interesting in Go, but we need to talk about them because we're going to talk a lot about slices. Because slices are what we use all the time in Go. And I'm not going to dig super far into exactly how slices work, but I'm going to answer the question that I had when I started working with Go, which is, okay, well, I've got this slice. How expensive is it for me to pass a very large slice between functions, right? If I've got a slice of 1,000 things, is it really expensive for me to pass that slice multiple functions deep, or how much work does the computer have to do when I pass slices around? And we're going to talk about the size of a slice and how much memory it takes up. And the first thing we need to know about slice is that slices really are a wrapper around an array, and when you pass a slice around, you actually pass this thing that is internally referred to as a slice header. And the slice header can really be, and it's often visualized as this sort of struct. It's not quite that, but you can imagine a slice header as a struct with 3 members in it, right? We've got a pointer to the underlying array. We've got how long that slice currently is and how big it could go, right? So here's how much data we've allocated, how much memory we've allocated. Here's how long we're currently using, and here's how big we can get before we need to allocate more. And that is all slices, no matter how big they are, always have the same length header because they always need to describe these 3 bits of information. So, answer my question, when I pass a slice, how much data am I passing? There's a lot of code here. Effectively, what we're doing is we're creating an empty slice of booleans and seeing how big it is, and then calculating how much memory is used under the hood. We're then going to make a slice of booleans that's already pre-allocated 100 booleans deep of memory, and then we're going to print that same information. And we can see that, yeah, the slice header is always 3 words, right? 888 is 24 bytes of data for me to describe a slice, no matter how much data, whether I've got 0 bytes of data inside or 1600 bytes of data. Passing a slice is always just a matter of copying 24 bytes of memory. So the answer to my question is pass slices all you want because you only pass that slice header. Keeping in mind, of course, that when you pass a slice, it's a pass of just that header, and there's no copy of the underlying data. It's a shallow copy. So if you pass a slice to a function, that function absolutely can modify data in that slice, and you wouldn't know about it. It doesn't even have to return the slice to you. It can just modifying the underlying data that is pointed to by the header. So it's very efficient, but also be careful if you don't trust the functions to not modify your data. Going back to our discoveries, all slice variables, no matter how big, are the same for a shallow copy. And I point out shallow copy again because the data could be modified, but it just doesn't actually cost more to pass a big slice or a small slice. And that's going to get important as we talk about strings. Before we talk about strings, let's talk quick about bytes, like a really, really low level bit of data in Go. Now, in Go, we've got an explicit type called a byte. And if you dig in, you'll find that actually byte is really just this wrapper and alias around a uint8, which makes sense, right? Because a byte is just 8 bits and a uint8 is just 8 bits. So in Go, they've wrapped a uint8 and called it a byte. They're just aliases. And this isn't the only time where one Go type is an alias to another lower level type. But I've got some kind of cool examples of different ways that I can declare bytes in Go as variables, right? So I can declare them using integers or hex or even runes, and we'll get back into what runes are. This will work most of the time, but not always. The compiler will warn you if you're trying to use a rune notation that can't fit in a byte, and we'll talk about that. Or even if we want to do bytes with binary notation, this is the most obvious way to declare, like this byte is these bits turned on, these bits turned off. But no matter how we declare it, we can iterate through and print and see that when we print these, no matter how we declared it, because bytes are an alias to uint8, the default stringification of uint8 is to print decimal notation of that byte, the underlying data, right? So even though we declared it in a bunch of different ways, it's always going to be a decimal number by default when we print it. And I really want to talk about bytes so we could talk about byte slices, strings, and runes, because that's where we use those, but in more interesting ways. So the first thing we'll talk about is a byte slice, because byte slices are one of the things we use a lot in Go, and especially when you're talking about lower level operations. When you're dealing with I/O or network operations, reading from disk, talking to the network, it's pretty much always byte slices because it's a really, really low level interface to data. So as an example, we ripped out from IOUtil, here's what the read file signature looks like, and it returns a byte slice. And if we do some JSON marshalling, it's going to return a byte slice. This is important, and we'll dig into why it does byte slices and not strings, right? This kind of can be frustrating at first, especially with JSON marshalling and unmarshalling. You're like, you look at it and you wonder, why don't you just give me a string? Why do you give me a byte slice? Why not give me a string? And there's good reason for this. Byte slices are important because although we use them at these low level, they're also really the data type that underlies runes and strings. So let's talk about those, starting with strings. So strings are byte slices under the hood, sort of, and we'll get into that. But what I've got here is some sample code where we create a string and we print out how big it is using, again, the unsafe type of. So how many bytes does this string take? And then we convert that string to a byte slice and ask, well, okay, we know that strings are kind of like byte slices under the hood. At least that's what I'm telling you. So what happens if we convert from a string to a byte slice? How big is it now? And this is why I use the qualifier kind of, because it's actually a bit bigger to have a byte slice, at least header-wise, than a string. And I'll wrap this all up here at the end, but bear with me. strings in Go can be thought of as a byte slice. They are a series of bytes, and they're immutable. And because they're immutable, they have basically their own kind of header. So we talked about the slice header before. That was a pointer and a length and a capacity. But strings have a slightly different header. Because they're immutable, there's no difference between how long they are now and how big they can get, because they can't get bigger than they are right now. They're a fixed size. They can't change. So when you take a big string and you add one letter to the end, Go actually creates an entire new set of memory for that string that's the full length of your previous one plus 1. It doesn't actually append to the end of a string, which is one of the reasons that string appending is actually pretty inefficient in Go. But this explains why when we ran this code from before, and I'll run it again, for our string we got 16 bytes, and for our slice header we got 24, because again, strings are like byte slices. They're very, very close, except for they are a fixed capacity. So there is no need to declare the capacity in a string header. Neither of those made sense, though. If we go back and we look at this example, right, this really, it's capital H and I. We know that that really only takes 2 bytes to describe. So both times it was first 16 bytes and then 24. So if I wanted to actually look at this and say, well, okay, yeah, the string and the slice have these headers and they're different sizes, but how much memory is the contents of each of those? We have to do a bit more work. And so if I ask myself, what is the true size of this string? We have to declare the string. We have to get the size of the header and the length of the string, because we know that the string is a byte slice. So however long it is, that's the number of bytes that it takes up in memory. And we add those two together, and we get the total size that the string takes up in memory. The next thing we do is when we convert that string to a byte slice, which we can do, we'll calculate the header length the same way. How much is the overhead to have a byte slice? Then we're going to say byte slices themselves have a capacity. Like they actually have a bunch of memory allocated that is not in use, but is allocated and ready for them to use. So we multiply the capacity and add that to the header in order to get the total size that the byte slice uses in memory. And this is actually pretty starkly different. So for a string, the total size in memory of our high string is 18 bytes. When we convert that high string into a byte slice, the total size is now 56 bytes, because we actually have basically 32 bytes of capacity, even though we're only using 2 of it right now. And that's just the way slices work. I'm not going to dig into slices and why they have this excess capacity, but it's for good reason. What I will do is summarize when you want to use the 2 types. So comparing strings and byte slices, strings are immutable. That is a feature. You can pass a string, and it's passed by copy, so that when you pass a string around, it can't be changed. If you pass a string from one function to another, the function you pass it to cannot change your string. That means there's also a little less overhead, because we don't have this kind of extra capacity hanging off the end of our string, but it is very inefficient if we're going to concat a big string lots of times, right? It's fine to add little strings and no big deal, but if you're going to build one really, really big string by adding one letter at a time or a few letters at a time, it's very inefficient. So if you're doing that, please use a bytes.buffer, or even better, strings.builder, which are explicitly designed about efficient string construction from small additions. But strings are great. We use them all the time. I absolutely, there's no reason not to use a string. Byte slices, although they have a little bit more overhead, like I said, this is the lowest possible level. They're way more efficient to add onto, because slices themselves are more efficient to append onto and manipulate. This is the thing you're going to use when you're dealing with low-level operations in Go. So that's the difference between the two. The next thing I want to talk about strings, because we know that strings are byte slices under the hood, or like them, we know that we can index them, right? We can index slices, be it byte or otherwise. And so if I declare this string that says I am a string, and I get index 3, it will look, in this example, it's going to work just fine, right? We get the byte at index 3, and it's 109. We know that bytes are alias to uint, right? So we get that, and that's not a surprise. It's a uint 8, and it's an M, right? 0, 1, 2, 3. Third index is an M. No big deal. That works great, except for when it doesn't. So one big gotcha that can come up when you're working with Go is, say we take that A, and instead of a regular A, we do an accent A. So it's now I am a string. We can still index it. It still looks like it's an index, that M is at index 3, right? And if we but if we print it out, we're going to get a different behavior. We'll say at index 3 is 161. It's still a uint 8, but it's not only is it not A, it's not accent A, it's not M, it's upside down question mark. And this can really get you, if you're indexing your strings, this can seem absolutely bonkers. So why did that happen? Now we know strings are byte slices, but it is possible for non-ASCII characters in Go to be made up, and just in computers in general, to be made up of multiple bytes. So we can kind of illuminate the problem by taking our IM string and IOM string and converting them both to byte slices and then printing those slices and printing the index. So if we do this, it'll actually make more sense. So they have the same first two, right? It's I, capital I, and space. Both of them start with the same, so 73 and 32. But where the normal full ASCII string, the third index is 109, what we see is that we actually have, at our third index here, we actually have 195 and 161. And that's because accent A in Go, it takes 2 bytes to describe. We have to describe an A and the symbol. And that's why when we got the third index, it was not what we expected. And we'll come back to how we fix this. Keep that in mind. I am going to come back. Before I can talk about how we fix that indexing problem, we need to talk about runes, because they are critical to our comprehension of characters and representation of code points in Go. So runes are the default type that you make when you use this single string. Right? One of the earliest mistakes every Go programmer makes is using single strings or single quotes to try to create a string, and the compiler yells at you and say, you have to have just a rune inside single quotes. You need to use double quotes for strings. And so we do that, right? And the interesting thing about Go is that you can absolutely, in those single quotes, you can do things as simple as like the character X, or you could do emoji. You could just paste that in your source code, or other symbols. And that'll work inside single quotes in Go. Go knows how to handle that and treat that differently than it would if it was a string. And this all works. You can paste this, you can run this code. I'm going to here. And if we print these by default, it's a bit weird. But runes are an alias to int32. So the default print format for int32, which they're an alias of, is to print decimal numbers, which is why they are these sometimes short, sometimes very long decimal numbers. But Go allows us to explicitly convert our runes into strings if we would like, in order to print the string version of those. So if we do that and we string each one of those, we can actually get those characters back in the same visual representation we expect. So let's do something more with that. Let's take these runes and strings and byte slices and convert to and from those three. And Go actually has explicit definitions in the spec of how you go between those three types and how they behave. And it defines that they should behave and they should be able to convert between each other. So there's a lot of stuff here. I won't read it. But effectively it's saying that it's absolutely fine to take a rune or byte slice or string and convert between the three. So let's do that, right? Let's declare just a plain old string with double quotes and then our runes from before. And let's, in the first case, just take our string and convert it to byte slice. That's valid. We can also go one step further and say, well, these runes can't go straight to byte slice, but you can take a rune, convert it to a string, then convert that to a byte slice, and start to understand just how much data it takes for each of what seems to be, in these bottom three, single character, how much data it really takes. And it turns out, in the example of the ASCII character X, it's 120. And it's just 1 byte. But smiley face emoji takes 4 bytes to describe, and the ni character takes 3. So a rune has it has to take at least 1 byte, but it has no upper limit. Runes take as many bytes as it takes to describe them. And that can really get you, especially in our case of the A versus accent A. So all of that stuff about runes and byte slices and strings, all to come around to our original problem. And this is the same code as before. How do I index? How do I get the third, what I would call a character, which is kind of a bit of a simplification, but most people just call that third character in the string. And the answer is you use a slice of runes. Now, we could take a string, and we know that we can convert it to a bunch of bytes, and then we can then take those bytes and then build runes by chunking them up. And Go knows how to do this for us automatically. So if we take our confusing string with an accent in it, we convert it to a slice of runes, and then we try to get the index 3 of that slice, it's going to actually work the way we expect. And we can see that, okay, it now knows that I is a rune, space is a rune, accent A, even though it's 2 bytes wide, is one rune, and then M is another rune. So when we index this as runes, we actually can get the M like we expected. Now note this big scary red thing here saying this is still not 100% reliable. And that's because there is nothing in the Go spec that says a string has to be printable characters. And I'm going to show you how this can bite you. So there's a lot here, bear with me, I'll explain. But effectively what I'm doing is I'm making a byte slice, and the first thing I'm putting in that byte slice is I space accent A, which we know is actually, 4 bytes under the hood. Then I'm going to explicitly append to that slice a null byte, which is not printable. It's nothing. There's no visual representation for nothing. Then I'm going to put the M at the end with a single M rune character, and I'm going to then further append, convert it to a string, and append a string. So at the end of the day, what we're going to see is S is still going to equal I am a string, and we'll try to index it. So this is more or less, this top part is a really fancy way to build I am a string in the variable S with this null byte stuck right in the middle, because we manually stuck the null byte in. And we'll see that even with our rune slice conversion, this, looking at it, you can't tell. There's no way that you could tell that, okay, I convert it to a slice runes, how does M suddenly not index 3 anymore? And that's because that null byte is in there, and it counts as a rune, but you can't see it because there's no visual representation for it. And this is a gotcha. I mean, most people don't deal with null bytes, and a lot of languages don't allow them at all, but Go does. Go says strings are simply a series of bytes. There is no requirement that those bytes be printable. Let's go to looping, and we'll kind of come full circle in 1 second to null bytes. But looping has the same sort of gotcha, right? If we were to take this Go Weston kanji, and we're using a raw string here, and between these backticks, it means take everything in here as just a raw series of bytes and stick that into the string constant. And if we iterate over that, we know now that strings are byte slices under the hood, and we know that each of these is some number of bytes, maybe 1 to 4. And if we iterate over this with the normal for iterator, we're going to get a bunch of weird stuff back, because any one of the bytes that it might take to represent one of these characters is either not printable on its own, or some sort of weird, if you convert it to ASCII, some sort of weird representation, right? So we know that this won't work. Just like with our indexing, we need to be careful about looping over strings. We can do the same trick, though. We can cast our string to a slice rune, and then use that same iteration with just a different type, right? So once that string is a slice rune, we can iterate over, and it looks a lot more like what we expected. We got now these int 32s, and when you print them out, they are the characters that we expect. Even better, use the range operator. Most of us, in fact, in Go don't use for loops with the explicit 3-section notation. We use range because range is incredibly powerful and really smart. Range knows in Go that when I'm iterating a string, I should convert that to a slice of bytes and iterate that slice. I shouldn't actually iterate the strings 1 byte at a time. So if we do this with range, we get, with less code, the same smart iteration of our string. And what's cool is that range is also smart about null bytes. So if we do the same thing where we build half the string, we stick in a null byte, this time with the 0b notation, and then we put the other half at the end, convert that to a string, and then iterate over it, you'll see that we still had an extra iteration. Just like when we did the index, there was an extra null rune in there, because Go it sees that byte is there, and it says, well, null byte is a rune on its own. But at least the iterator was smart. And it didn't get mixed up, it didn't get weird characters, it knows where the boundaries are between each rune and even null bytes. Most of the time, most of us don't have to worry about null bytes, but be aware that they exist, and that even if it might look correct when you print it out, there could still be data in your string that you're not aware of because it's not printable. So that's going to be the takeaway here. Be careful when you're indexing or looping a string, because it might behave in ways that you don't expect, and you might be able to print it and think it should be this, but it's not. So let's talk about structs. We've already dealt with structs a little bit, because remember we said string headers and slice headers are kind of like structs, but structs are the way Go organizes data. They are not objects, and that distinction is important because in Go, structs they're not objects, they're just groups of data, and they have no overhead at all. And we'll get into exactly how that's useful later. But we can declare structs in a couple different ways and see that this absolutely works. This is an interesting code, but we'll get there. One thing about structs is they are usually as big as their fields combined. So I've got 8 bytes in a uint64 and 8 bytes in another uint64 here, and if I add those two together, I'll get a total of 16 bytes. This isn't a surprise, right? There's no overhead, so the struct doesn't cost us anything to have, and it's just the width of the two things inside of it. Even if I were to take a struct and nest another struct inside of it, it's going to be the width of the things in just the data. There's 2 structs here, but there's 0 overhead for those 2 structs. And if we run the code to add all that together, we do indeed get 32. But not always. Structs are not always exactly the width of their members. So if we say, well, okay, I've got these 2 uint64s, I would like to save some space, so I'm going to convert one of them to an uint32 because I don't need that other 4 bytes of capacity. And that'll save me 4 bytes, right? Like my struct is 4 bytes smaller now. And if we get the size of each of these members and add it up together, it's still 16. And this is a bit weird at first, and it's not a Go specific thing, but for me, and digging into types the first time, this was a shocker. What Go wants to do, and if you go dig in, is that Go and most languages really want data structures to be naturally aligned. They want it to be on word boundaries, right? And we talk about word boundaries being architecture dependent. So in my case, I'm on a 64-bit system. It wants to be 8 bytes or 64 bits of word. I kind of think of this as like the system has a 8-byte wide shovel, and it wants to shovel 8 bytes. It really has to shovel 8 bytes of data at a time. And it's much more convenient to shovel 8 and just kind of throw half of it away than it is to try to shovel just half a shovel's worth. So that's the way I think of this alignment. And this is another case where you can imagine the compiler rewriting your code for you right before it compiles. And so it says, okay, well, I want to align things on 8-byte boundaries. So you've got 4 here. I'm going to fill in 4 more, and that's going to be 8. That'll get us to 16, which is a multiple of 8, and it fits my shovel. And so that's why when we ran this previous code, we had 16 bytes. Now what's cool is if I take that example and turn both of them to uint32s, now 4 plus 4 is 8 bytes. It fits that word boundary, so there's no padding required anymore, because now when you add those up, they're already nice and even on an 8-byte boundary, and so we actually do get that compression and we get half the space that we did before. Most of us don't have to deal with this on a daily basis, but if you're trying to get really high performant, really efficient Go, this can matter a lot, and it can matter even more in some other examples. So let's take our Boolean example. Now we know from the very beginning of the talk that Booleans are 1 byte wide, and we know from just before that there's going to be padding. So if we create a bool, it's going to take up 1 byte. It's going to want to pad us to 7 so that we have 16 total. And if we run the code to get the size of each of these, we see, yes, the bool took up 1, and the uint64 took up 8, and total, the thing takes 16. Those don't add up, but that's because there's 7 bytes of padding added for us by the compiler. But the compiler's smart, and it doesn't add more padding than is necessary. So you can fit more things. In our case, I'm going to stick 1 more bool in here. And if we say, well, I'm going to use 1 byte out of that 7 bytes of padding for another bool, it's still 16 bytes of memory, even though I've got another bit of data. So this is another case where I can actually put more data in the, no matter what I do, and I can use that buffer, and it doesn't cost me more in the system to do the copies, because it's already filled out with this buffer, and whether you use it or not is up to you. This can also work against you, by the way, in the next example. So if I take that same struct, 1 uint64 and 2 bools, and all I do is put 1 bool in front of the uint64 and 1 bool after, the compiler says, well, I need to make all of this line up on boundaries, and so I need to give you 7 bytes so that we line up on a boundary for here, and then you've got 1 trailing byte, so I need 7 more bytes. And indeed, just shuffling the 2 bools we had, we didn't change any of the data stored, we just changed how they were described in the code, has resulted in 8 more bytes being used. Right, and this, for most of us, this doesn't matter, but when you get really efficient, you start to have to look at your code and understand, well, where's padding coming in, and is it going to add extra data? And if I declare this in just a slightly different way, I might save myself a bunch of memory. So that's something cool about bytes and padding, and again, that's not Go specific. Let's talk a bit more about structs. I breezed right by that empty struct thing at the beginning, and we talked about that structs have no overhead. They're not quite objects, they're just data groups. So do they really have no overhead? Is there like a struct header or something that, like when I pass an empty struct around, what am I passing? Right? Because you can do that. You can send an empty struct to a function, no big deal, it'll take it. And it turns out you're passing nothing. You can absolutely create an empty struct and get the size of it, and it's going to be 0. Empty structs take no space. There's no header. There's nothing. Even if I have an empty struct full of more structs, as long as every struct inside my empty struct is empty, it's always 0. I could build a million layers deep. It's going to take 0 memory. I could create an array. And remember, arrays are a fixed width. It's going to say pre-allocate space and memory for that array. I'm going to create an array of 100 empty structs. And the size of that, 0. Because 100 times 0 is still 0. This is mostly silly, but I promise there's a point. Interesting thing about, we know that this empty struct array is 0 size, and empty struct slice is actually not 0 size. So if I make an empty struct slice of 100, we know underlying it is the array underneath that slice is 0. But if we get the size of the slice, it's still that 3-word slice header, right? It's still a pointer to memory, a width and a length, even though the pointer is to a 0 bytes array. The width is 0 and the capacity is 0. It actually is. This is 100% not important, but it's an interesting ephemera thing. A slice of empty structs takes memory, which is weird if you really think about it. So ephemera aside, what's the important part? Empty structs are incredibly useful as sort of a code signal, and sometimes even as a memory saver. So let's start about the code signal first. I've got an example here where I've got a very, very simple Go concurrency example where I make a channel of empty structs, and then I spin off a function that sleeps for a second and then sends an empty struct. You have to do this kind of, I have an empty struct and I want to create a new one. So there's these double braces are not a typo. That's what empty struct creation looks like. And I'm going to send that to my channel of done, and I'm going to wait for a signal on that channel and print done. Now this is not super interesting results, but what happens in here is if I have a channel, say, and it's more complicated code, and inside this channel, the type of data sent along that channel is nothing. That's useful for me as a code reader later, because I can look at this. If, say, instead of using an empty struct here, I used a Boolean, and I come back at it a month later, I have to wonder, well, there's a Boolean in this channel. Does true mean something different from false? When I get data from this channel, if I get a true, should I treat it different from a false, or do I just want any value? That might not be that bad, but if you're got a big code base, it could be very useful to look at this and go, well, this channel gets a signal. It gets like a ping effectively, but there's no content. Like there is no true false. It just got a note. It just got a signal, got a ping. So I don't actually have to worry about the content. I know that this channel is purely for signaling, and that's where you see empty structs used. The other case, and I'm going to close this so you can see it, the other potentially very large space-saving case is in maps. There's a lot of tricks where if you want to count, say, unique words in a string, you might use a map of string and let go's map deduplication kind of help you count unique things, right? You just add to the map and set it to true or false. And people tend to use bools in these cases where they don't really care about the value because they think bool's small. And we know that bool isn't actually a bit, right? It's a whole byte. So imagine I'm counting and I've got 1,000 unique words in a string. Using empty struct in that map instead of Boolean could save me 8,000 bits or 1,000 bytes of data. And that can add up very quickly. And again, signals that I don't care in this map. I'm using the map purely for the uniqueness of the keys, and I don't care about the data. And that's when empty structs are very valuable, is for code signaling and sometimes saving just a little bit of space. So, coming back to learning 8, structs have no overhead, but might have padding. So they might take more space than you think, or not at all, depending on how you use them. Let's talk about maps real quick. And maps don't belong in this talk. It turns out, if you dig into Go, maps aren't a type. They're not a low-level type of Go. Like, really, they're not. I know we create them. We create maps, we put them in structs, we send them to functions. But it turns out that if you dig into maps, and I'm not going to because that's well outside the scope of what I can cover here, but if you dig into maps, they are essentially generated structs that are kind of plumbed in for you automatically by the compiler. So right during compilation, when the compiler sees things like this on the left, where we're getting values from maps, we're assigning values to maps, that kind of stuff, what the compiler does is rewrite your code. Again, like it's done so many times for us today so far. It rewrites the code to actually use the runtime package and some dynamically generated structs. So maps aren't a low-level type. They're just sugar around other low-level types like structs and functions and packages. If you're curious about that, by the way, you can go read up on Dave Cheney's detailed explanation of how maps work. I'm not going to cover it here, but it's really cool. So another discovery about types specifically is that maps aren't one. Just like IOTA. Turns out that maps aren't a type in Go. It's just something you might think of as a type. On to interfaces. Interfaces are, I'm not going to cover too much of what they are, but I ask myself, when I pass interfaces around in functions, am I passing a lot of data or a little or none, or like how expensive or efficient is it to pass interfaces? And it turns out that in Go, interfaces are really just two words, no matter what is behind the interface. If you receive or pass an interface, you are sending two words, in my case 8 bytes and 8 bytes, of data. One is a pointer to what kind of thing is behind the interface, and the other is a pointer to the actual data. Right? So if I pass an interface that is actually in front of a string, then there's going to be one pointer that says, go over here to find out that this is a string I just gave you, and another says, go over here to find out where the data for that string lives. And that's it. So interfaces are very, very efficient to pass around and Go. They're as efficient as strings. And I've got a kind of a quick code example here that explains no matter what we pass, whether we pass a true constant or 1 or an int32 or an int64 or a string, we're going to print the size in bytes of the interface and the type. And we can see pretty clearly here that the interface is always 16 bytes because it's two words. And no matter what, it's always that same width, right? 16, 16, 16, even though the rest of this changes depending on exactly what we've passed. The width of this changes for different types. So when we passed, say an int64, for example, it's 16 bytes. So pass interfaces all you want is sort of the takeaway here. They are very efficient. It doesn't cost a lot to pass. And by the way, these two pointers that pointer to what I just gave you and where the data is, that's how the reflect package works. Reflect package just says, okay, follow that first pointer to find out what you just got and then get the size of that thing. So reflect is not, I mean, it's cool, but it's not super magic. It's literally just following the pointer that's part of the data you just gave it. The kind of real tricky thing, and one of the questions I asked at the very beginning of the presentation was, when is nil not a nil? Are all nils equal? And it turns out when it comes to interface nils, they're not. So what I've got here is I'm creating x, which is a pointer to an integer, and I'm creating y, which is an empty interface, which is nil. There's nothing. There's nothing there. It's a pointer to nothing and nothing. And I'm going to say, is x nil? Print true or false. Is y nil? Print true or false. Is x equal to y? And then print the result. And individually, x is nil. And y is nil. But x does not equal y, because the interface nil is, like I said, a pointer to 2 bits of data, and so it's actually kind of, I'm not going to dig too much into it, but you think of it like 2 nils, right? Because there's 2 pointers in there. And so there might be cases where you print out 2 pointers, and one of them is a pointer to an interface, and they both print as nil, but they're not actually both nil. And that's kind of a trick. So discovery 10 here is interface nil isn't a nil, which could really get you in some places. Most of us won't hit that. That's partially an ephemera thing, but still cool to know. So that's it. I hopefully you enjoyed watching. I will kind of plug the presentation tools that I use. So I am using GoPresent. It's really cool. It lets you write Markdown, where you write Markdown for your slides, and then you can reference sections or entire Go files. And those Go files are fully compilable and runnable. It's sort of taking the Go concepts of how you do tests and taking it all the way to, well, how do you do presentations? We write Go files and then you run them like normal. I'll also kind of take a quick second and point out this extension that I made. Because this presentation has a ton of individual tiny Go files with references in the Markdown, I got really sick of finding the individual files, so I just like to plug, if you use VS Code and you're doing a big presentation with GoPresent, I've got an extension that lets you control-click on the references to code files, and it will open them in a peek. So kind of nice if you're using GoPresent. Again, thank you so much. My name is Carson Anderson. I'm a DevX engineer at Weave. I'm on Twitter at Carson_ops. I'm on GitHub at Carsonoid, and that's where I have the source code for this presentation. So this presentation and all of the code examples, you can pull it down, you can run GoPresent, you can walk through it just like I did, read the slides at your own pace, edit them, all of that stuff. It's all my presentations are always fully open source. So hopefully you appreciated that, and thank you so much for spending your time with me.